Hi everyone. In our last video, we had discussed the liquid-liquid equilibrium diagrams. Today, we look at the relationship between the two phases which are formed in liquid itself, liquid phase itself. So let's discuss the liquid-liquid equilibrium. So many pairs of chemical species where they to mix to form a single liquid phase in a certain range of composition would not satisfy the criteria of stability. So the criteria of stability is that the Gibbs free energy must be minimum and the double differential of Gibbs free energy with respect to x1 at constant temperature and pressure must be greater than equal to 0. If it is equal to 0 तो आपको क्या मिलेगा? We are getting the unstable state or unstable phase जो मैंने आपको last diagram में explain किया था कि कहाँ पर आपको unstable state मिल रहा है, right? So such system therefore splits in this composition range into two liquid phases of different composition, right? So वो splits हो जाते हैं two their composition must be different and they splits into two liquid phases. Okay, they are not separating into other phases, they are splitting into liquid phases only. Okay, if the phases are at thermodynamic equilibrium then this phenomena is known as liquid-liquid equilibrium. Okay, so हमने लास्ट टाइम जो डायग्राम डिस्कस किया था तो क्या डिस्कस किया था? वी हैव ड्रॉन द डेल्टा जी वर्सेस x1, राइट? सो आपके दो ग्राफ, हमको एक तो ग्राफ ये था जो आपको सिंगल फेज जहां पर सिर्फ ओनली वन फेज इज देयर एंड वन डायग्राम विल बी लाइक दिस, राइट? और यहाँ पर बिकॉज बिकॉज गिव्स फ्री एनर्जी इज मैक्सिमम एट दिस पॉइंट, हमें स्टेबिलिटी के लिए क्या चाहिए? इट शुड बी मिनिमम. तो यहाँ पर वो मिनिमम, तो इन दिस ग्राफ यहाँ पर मिनिमम बट हियर इट इज मैक्सिमम. सो यहाँ पर जब वो मैक्सिमम हो जाती है गिव्स फ्री एनर्जी तो वो क्या करते हैं, जो सॉल्यूशन है वो क्या हो जाता है? स्प्लिट हो जाता है इनटू टू फेजेस. दोनों फेज किसमें? लिक्विड फेज में ही है बट इट splits into two phases, and if the phases are at thermodynamic equilibrium then this phenomena is known as liquid-liquid equilibrium. So and this liquid-liquid equilibrium, it is used in solvent extraction at constant temperature and pressure. So we denote the liquid phase by, here we denote the liquid phase by alpha and beta, liquid phase by alpha and beta, right? And equilibrium criteria is if the system is in equilibrium तो क्या होना चाहिए? Fugacity of alpha phase must be same in the beta phase, right? Or pressure in alpha should be equal to the beta phase. तो ये कौन सा हो गया? मैकेनिकल इक्विलिब्रियम हो गया, ये केमिकल इक्विलिब्रियम हो गया. एंड सिमिलरली थर्मल इक्विलिब्रियम के लिए टेम्परेचर भी क्या होना चाहिए? सेम होना चाहिए. सो अगर आपका सिस्टम इक्विलिब्रियम में है तो ये तीनों कंडीशन को उसको सेटिस्फाई करना चाहिए, राइट? सो लेट्स टेक दिस इज योर equation number 1, and here I denotes the number of species 1 2 3 and n number of species can be there. Now with the introduction of activity coefficient for activity xi alpha, gamma I alpha, fi alpha is equals to xi beta, gamma I beta and fi beta. This is, let's take this is equation number 2. If each pure species can exist as liquid at temperature of a system then the fugacity of liquid will be same, right? Is equals to fi. Why? Because each pure species can exist as liquid at टेम्परेचर ऑफ सिस्टम टेम्परेचर और टेम्परेचर ऑफ सिस्टम, राइट। तो वहां पर फुगैसिटी होगा ही नहीं, तो फुगैसिटी क्या होगी, अल्फा एंड बीटा फेज में वो आएगी नहीं, प्योर स्पीसीज है, तो उनकी जो अगर वो प्योर स्पीसीज हैं तो ऑफ कोर्स इफ इट इज इन द लिक्विड फेज तो वहां पर फुगैसिटी टर्म होगा ही नहीं, द फुगैसिटी विल बी remain same, the fugacity of alpha is and alpha phase and the fugacity in the beta phase will be same. So that's why therefore xi alpha gamma I alpha and ये दोनों क्या हो जाएंगे, cancel out हो जाएंगे because they are same, is equals to x, this is alpha, xi beta is equals to gamma I beta. Okay, so this is, let's take our first relationship. Let's take, this is the third relationship, third equation, and this is our relationship. Now I, you know that there must be one, two, or number of species can be present. So now we know that activity is the function of temperature, pressure, and composition, right? So we can write for activity for alpha phase as gamma I, temperature, pressure, and x1 x2 कहाँ तक जाएगा, n minus 1, fine. Similarly gamma I beta is equals to gamma I, temperature, pressure, 1 2 3, number of species n minus 1. So this is let's take 4 and 5th. Now according to the equation number 3, an equilibrium condition can be written in 2n intensive variables. So 2n, see, and see, according to equation number 3rd, so an equilibrium condition can be written in 2n intensive, or let's take capital, intensive variables. And intensive variables क्या क्या है, temperature, pressure, and n minus 1 independent mole fraction of each phase, mole fraction of each phase. And this is according to phase rule, and this is according to phase rule. So we know that degree of freedom F is equals to C minus P plus 2, right? And we know that हमने यहाँ पर components को कैसे denote किया है, by n, small n, right? And phases, we know that कितने phases हैं, 2 phases are there. So you can substitute the value over here. So n minus 2 plus 2. So 2 cancel हो गया. So degree of freedom क्या आ गया, is equals to number of components. And same result we can obtain for vapor liquid equilibrium also. So for any binary solution, from equation number 3, हम कैसे लिख सकते हैं, x1 alpha gamma 1 alpha is equals to x1 beta gamma 1 beta. Okay, let's take this as the equation number 6. Similarly, you can write for the component 2 because we have binary solution. So x2 alpha gamma 2 alpha x2 beta gamma 2 beta, right? And you can also write x2 in terms of, we know that x1 plus x2 is equals to 1. So in place of x2 you can write 1 minus x1. So replace this x2 by 1 minus x1 and 1 minus x2. So you can write in that way also. And we know that gamma 1, which gamma 1 is the activity coefficient in alpha phase. So we know that this is the function of temperature, pressure, and mole fraction. Similarly, we know that gamma 1 beta is equals to temperature, pressure and x1 beta. Okay, so now just taking a log of equation number 6 and 7. So 6 and 7, or you can write this 1 minus x1 gamma 2 alpha, or 1 minus x1 gamma 2, this is beta, sorry, and this is alpha gamma 2 beta. Now let's take, this is the equation number 8. So now just take log of equation number 6 and equation number 8. So you will get the final relation, which is gamma ln of gamma alpha upon gamma beta is equals to ln of x1 beta upon x1 alpha, right? And similarly, ln of gamma 2 alpha upon gamma 2 beta is equals to ln of 1 minus x1 beta upon 1 minus x1 alpha. So these are the two final relation for the liquid-liquid equilibrium, and these are the relationship between the activity coefficient, right? Activity coefficient gamma 1 and gamma 2 and mole fraction x1 and x2, right, in alpha phase and beta phase. In liquid-liquid equilibrium, just remember one thing, if सिस्टम आपने मिक्स किया है, सोल्यूशन बनाने की कोशिश कर रहे हो, और अगर उसकी गिव्स फ्री एनर्जी इज नॉट मिनिमम, देन अगर वो स्टेबिलिटी क्राइटेरियाज जो हमारे टू स्टेबिलिटी क्राइटेरियाज है उसको अगर वो सेटिस्फाइड नहीं कर रहा है आपका सिस्टम और सोल्यूशन, देन वो क्या करेगा, लिक्विड वहां पर स्प्लिट्स हो जाता है इन टू लिक्विड फेजेस, एंड यहाँ पर हमने उन लिक्विड फेजेस को कैसे डिनोट किया है, थ्रू अल्फा एंड बीटा फेजेस. ओके, एंड एट डिफरेंट मोल फ्रैक्शन, जो कंपोजिशन था वो भी क्या हो जाएगा, उनका डिफरेंट हो जाएगा. सो यहाँ पर जो अगर अल्फा फेज है तो x1 मोल फ्रैक्शन इन अल्फा फेज एंड मोल फ्रैक्शन इन बीटा फेज, राइट. तो जब आपका सॉल्वेंट एक्सट्रैक्शन जब आप करते हो, देन वी यूज दिस लिक्विड लिक्विड इक्विलिब्रियम प्रोसेस, वहां पर ये एप्लीकेबल होता है. एंड वी हैव ऑलरेडी डिस्कस द वन diagram, LLE diagram, where we have two states. One is the three states, in fact, unstable state in the center of the diagram, and then we have metastable, and then we have a stable state. External curve hota hai, that is called the binodal curve, and the curve which separate the unstable and metastable state is known as synodal curve. Thank you.